Alright, we want to start looking today at logarithms and what those are and how they work. So, first activity here, I'm just given a random set of numbers to find the log of, and you can do that right now just by using your calculator. The log button is right there. If you go log 1,000, you come up with 3. Now what we're going to do here is we're just going to calculate the log of a bunch of numbers and try to see if we can get a feeling for what might be going on in terms of what a log does to a number. So if you continue on with this, I've actually picked numbers here where the log of these numbers produce nice answers. You can do this yourself just to check. If you go to the log of 0, log 0 is error, undefined. There is no answer, so we'll have to investigate that. Let's try log negative 10, and that is also undefined. Alright, so again we will figure out why that is, but just as a starting point, you might notice that the numbers I've picked all have something to do with a base of 10. And so the way a log actually works is that in the case of this log, I can think of this as being a rewrite of an exponential form of 10 to the third is 1,000. Okay? A log is just a different way to write an exponent. So for this one, it's a base of 10. And you might say, well, why is it a base of 10? Well, I mean, we can see that these numbers are all related to powers of 10. But you can think of your little log as having a little subscript of 10 there. And then you can transfer it over as 10 to the exponent 2 is 100. This means the same as this. We have 10. The answer to a log is an exponent, which is hopefully what you're figuring out, equals the thing in this position, 10. Okay, so 10 to the first is 10. Okay, base of 10 to the exponent 0 is 1. Yes, that's true. 10 to the negative 1 is 1/10, which as a decimal is that. 10 to the negative 2. Alright, so a log is a different way to write an exponent. Now when we come down to these last two, the log of 0 is apparently undefined according to the calculator. Let's just try to see if we can reason that out. So based on what we've done here, that would be 10 to the something is equal to 0. And if you ask yourself, if I do 10 to any exponent, will I ever get 0? Even if I do 10 to a negative exponent, remember we get a fraction, but we don't get 0. So even a negative exponent is never going to produce an output value of 0, which thus means that the log of 0 is undefined. We can't log 0. Okay, and similarly for this one, what's the answer to this? This would be 10 to the something is negative 10. And there's no exponent we could put in that would produce a negative answer. Alright, so hopefully that gives you a little bit of a feeling for how logs work. And so now we're ready to do a definition of a log. And that goes like this. The log base A of x equals y. Now in the questions I did in the previous page, there was no little number written down here. And when there's no little number written down there, we assume that that's a base of 10. So on the previous examples, everything was related to a base of 10. That's why I was using a base of 10. But the number down here doesn't have to be 10. It can be a base value a, let's say. And the transferring over process to exponential form works the same. It's a. The answer to a log is the exponent, and that's equal to x. So this is the exponent, this is the base, the argument of the log, the thing we're logging, goes there. And logs do have restrictions. You'll notice on the questions we did in the last page that when we tried to log 0 in negatives, it didn't work. So our restriction is that x is greater than 0. We've also talked, when we talked about exponential functions, that we always use a positive base. So we're going to restrict our base to a being greater than 0. And later on, we'll also learn that a can't be 1. Okay, more about that later. But for now, that's your definition of logs. Alright, now I should mention that the log button on your calculator is a base 10 log, which means that this number in this position has to be a 10. And if it's a 10, we often don't write it, as you saw in the previous questions. Okay, but if it's a log base 4, as this question is, we have to come up with some other ways to evaluate this. But in this case, we're being asked to do it exactly, which means the answer works out evenly and we don't need to use our calculator. So when we do a log question, we go back to the definition of what a log is. Remember that this means that 4 to the something power is 16. You just say that to yourself, 4 to the what is 16, and the answer is 2. 5 to the something is 1 over 25. If you think about that for a second, that's an exponent of negative 2. Now we're able to do these two logs without a calculator because they are numbers that work out nicely. Later we'll talk about doing the log of a number that doesn't work out nicely and how that works with the calculator when you have non-base 10 logs. Okay, a couple of other little questions to learn about here. We want to do the log of this expression. So probably what you would do is follow your order of operations. You would probably say log base 3 of 9. So you're basically saying to yourself, 3 to the second is what? It's 9. Now you're going to log that. So you're going to say 3 to what power is 9? And you'll notice that that's 2. Okay, I'm going to do this one more time. Just think about what you're thinking as you do this statement. So the first thing I'm going to do is I'm going to say 4 to the second exponent is what? Well, that's 16. Now I'm doing a log, so I say 4 to the what exponent is 16, and I say to myself, well, that's 2. Okay? Do you get a feeling that what you were thinking in the first step and the second step are inverse operations of each other? You're doing the reverse operation in each step. So you're saying 4 to the second is 16, and then you're saying 4 to what power is 16, and you get 2. And the point here is that if you have a log base A, and then you take the log base A of that same base A to the n, you are going to get n back again. Notice that these match. That means that the answer is going to be the 2. Okay, so that's one of our inverse properties. We can also do this in the other order. Okay, so this looks like a complex little expression here, but let's just follow it through. So we got to start with the exponent. Log base 3 of 9. Remember, this means 3 to what exponent is 9? Well, that would be 2. And then we're saying, what's 3 to the exponent 2? Well, that's 9. Okay? Can you get the feeling of an inverse happening in the two steps of this problem? Again, let's do this again. So we're going to do the log first. This means 4 to what exponent is 16? Well, that would be 2. And then we're saying, well, what's 4 to the 2? We're undoing what we just did. And guess what? We're back to what we started with. What we started with comes back when we do the log and then we do the exponent. And so we can generalize that by saying that if we have a base of A and our exponent is log base A to something that we're able to do, that will be n. And of course, both of these statements are true for valid values of the variables. All right, let's apply our understanding of logs to the solving of some simple equations. All right, so most of the time when you solve an equation, what you're going to do is apply the definition. So I have a log here, so I'm going to turn this into exponential form since I'm more familiar with working with exponential form. So I think of my base of 4 to the exponent negative 2 is equal to x. X is isolated, so I've solved, which is 1 over 16. And now the only other thing I need to check is when I substitute this back in, I got to make sure that what I have here is a number greater than 0, because remember, that's the restriction for logs. I do, so we should be good. All right, and one more question, but this time we have our x in another position. Our x is the base. Now we got to keep in mind here that restrictions for the base, if you go back to the definition, are that x must be greater than 0 and x cannot be 1. Alright, so let's apply our definition. We could say that x to the negative 2/3 is equal to 9. Alright, so what I'm going to do to remove the negative 2/3 exponent is I can raise both sides to the negative 3/2 exponent. Because when I multiply exponents I get x to the 1. And here I'm going to get 1/9 to the 3/2, which is 1 over, remember this is the square root of 9 cubed. This is 3 to the 3rd, 27. It meets these conditions, so this is my answer.